Okay, so welcome everyone to the first webinar in the new series, coming to you with the support from EECA Business. So these free webinar series will be available free of charge for anyone that wants to tune in. So welcome, thank you everyone for joining us today. It's great to have the support of EECA in continuing the webinars that we've done in the past. So today's webinar is a bit of a review and a sort of an introduction, if you like, to fan systems. Now, joining me today on the panel is Dr. Martin Atkins, who's here. So as we're going through the webinar, if you have any questions that you would like to throw up, you don't need to wait till the end. Feel free to through the portal there, you'll see you can fire in some questions, and then as appropriate, Martin will either answer them direct or he'll bring them to our attention, and we'll integrate them into the presentation as we go through today. So by all means, just to reiterate, feel free to fire through questions as we go today, and where appropriate, if you've got a mic, we can let you pose your question to the group or restate your question, and we'll go from there. So without any further ado, we'll get underway. So today's webinar, entitled Industrial Fan System Assessments for Energy Reduction, and really about getting started. Where do we begin and where do we get started? So as a bit of an overview today, we're going to sort of just talk a little bit about why fan systems, talk about a few definitions to help us to understand what we should be looking at and why, and how it all fits together. Talk a little bit about, well, what does constitute an assessment versus an audit, a little bit on fan sizing, talking about energy efficiency in terms of, well, looking at the system as a whole and the things that we need to consider, and then obviously getting started. And then as we get started, we're going to break things down into sort of 4 levels of system optimization that we can look at. Okay, so first things first, I guess the first question that comes to mind is why fan systems? Okay, well, why fan systems? Well, it's 10 to 15% of industrial electrical demand. In New Zealand, it's around 5% of total electricity usage. Okay, and the majority of fans, they're oversized. And 10% of fans are oversized by 60% or more. There's typically some large savings opportunities there, not just in energy, also maintenance, capital costs, and so forth. The other good thing about fan systems is there's a lot of common problems that have common solutions, and so it's sort of a broad application with some good gains to be made. And obviously a key part of realizing those gains and locking them in is taking a systems approach to these systems. Okay, so let's take a step back for a minute and just sort of think about, well, what does constitute the fan system? And what we're really saying is fans never sit in isolation just moving some air or some other gas around. Generally, they're connected to something. It may well be a process where you're obviously transporting some sort of gas stream around, part of some sort of reaction or extraction system. May well be a combustion system, a dryer, or some other reaction vessel. You've then got sort of utility systems. It might be just some heating or some cooling or just straight ventilation. It might be a health and safety application in terms of providing a clean atmosphere. There's a whole host of potential scenarios, but the key thing in each of these is seldom, if ever, is the fan just sitting there in isolation. It will be doing a job or performing some function, and it's very important that you consider the bigger picture of what that function is and not just zero on the fan itself. Okay, so the other thing to think about as we look at the system is to understand the different components. So you obviously have the fan unit itself, the impeller, housing, your drive system, your motor may have a gearbox or some other coupling, drive ratios, etc., belts, pulleys, and so forth. You've then got the ancillary equipment that's often connected with those fans. So you might have inlet filtration or exhaust filtration, might have the form of cyclones, bag houses, some high temperature applications you might have sort of ceramic based filters or other such devices. But all of those become a critical part of the system. You've then got obviously heat exchangers where you might be heating, cooling, or humidifying or dehumidifying the process streams. You've got all the ducting that connects the various bits together. But the key thing down the bottom there is you've got whatever the system is hooked up to. Is it a process, a reactor, or a dryer, etc.? All of these systems actually need to be considered as a whole. Okay, then you've got the control system. How are you actually controlling those fans? So if you think about it, here's a really simple device. You may have a single fan. You could have fans in parallel. They may well be in series or a combination of the both. So you've got there down the bottom some sort of fan intake, may or may not have some intake filtration. You bring the air in, the fan's obviously providing the static head you need to move the gear around. That might be going to multiple air handling units being used for various things. Various control valves, that may be an open system or a closed system. You might have some recirculation with sort of fresh air added in. But the key thing is if you think of the red box there, if we just put a boundary around the fan itself, the most efficient way of running that fan may not be the most efficient way of running that system. Okay, and so it all comes back to, well, what is our system's function and what's the most efficient way to perform that function. So just to remind everyone that it's important that we can recognize and differentiate between, you may have an open system, i.e. sort of air in and out and relatively straightforward. Generally in open systems you'll have what we refer to as a constant reference static pressure. So this is, if you think about a system like this, it might be all out in the open like the picture just there. And if we plot the static pressure through that system, you'll start off obviously open air at the front end, so reference pressure of atmospheric pressure. The back end, we've also got a reference pressure of atmosphere, obviously going in and out. You got some sort of inlet losses across some duct work. You might have some sort of recuperator or preheater. You'll notice with duct expansion you might get a little bit of pressure recovery. Then as the air is accelerated again, obviously you're then requiring more static pressure. You've then got losses across filters, intake ducts, etc. And ultimately you've got some sort of negative pressure at the intake to your fan. Obviously your fan is then giving you your positive pressure, and then you've got your various pressure drops. Once again, if you're expanding the flow in a duct before a heat exchanger, you might get a little bit of static pressure recovery as you slow the air down. Then you got your pressure drop across your various vessels and cyclones or bag houses or whatever may be in the mix. The key thing being through all of this is when it comes to assessing and measuring the system, you've got a constant reference pressure, so it's relatively straightforward to assess where all your losses are in the system. Now, of course, there are some times, and I guess the food industry here in New Zealand is a really good example, where actually you're trying to maintain a controlled atmosphere. And so you may have multiple segregated areas in your process or building, which will be at different static pressures. And so as you assess a system, it's important to realize that as you go through the same system, you'll have different reference pressures. So as you're comparing measurements, it's important to understand how things vary and how things might change. Okay, to bear that in mind, otherwise you could be making some rather silly and potentially embarrassing or costly assumptions that may not be correct. And so this is where you might have multiple regions, say A, B, C, D here in this example, where you've got different reference pressures that you need to bear in mind as you do an assessment and look at the system. Okay, and so what you have is each of your boxes or transition zones there, you have a change in the reference pressure. Okay, so what we're going to do is we're going to, as we think about our fan systems, we're going to backtrack a little bit and look at how our systems need to be assessed. And what we like to do is use a compressed air analogy. And what we mean by this is, in compressed air, we generally talk about the supply and the demand side of the system. The demand side being actually the end use or purpose. And so this is where what we're really saying is the number one thing to think about here is, well, what is our actual demand and on our fan system? And that demand is typically going to be whatever our end use is or purpose of the gas, which is normally air, not always, but typically. Okay, and what are we doing with that air? If it's a dust extraction system, or it could be a process heating requirement where you're trying to dry something, you know, the question is what are you wanting the air to do? So it'll be perhaps a certain air flow rate at a certain temperature, or it might be providing a certain suction to remove or convey a waste material away. The key bit thing being is the purpose is not actually the power consumption of the fan per se, but it's what you're actually trying to do, and it will typically be a volume of air at a certain pressure of some description. We've then got a distribution network that we need to consider in terms of, well, where does the air and particulates, if they're picking up particulates, or the heat get conveyed? Can it be recovered? You know, there's a whole network here in terms of ductwork. There'll be flow control dampers in some situations. Sometimes it's very important to also consider isolation points. There's plenty of applications out there where the airstream, as you pick up particulates or waste, can actually then pose a fire risk, and so you start to need to then also give consideration to isolation points that might be for safety or for cleaning. You might have explosion vents and divert dampers. All of these things become a critical part of the system and are all potential failure modes or points that can cause inefficiencies. Then ultimately, you've then got the supply side of the system, meaning, well, where's the air coming from? How's it being moved, recycled? You've got the fan assembly itself. And I guess ultimately, at the end of the day, you know, in terms of the pop quiz for you guys, where do we start first? And this is where, just like with compressed air, you know, the trap to fall into is you think it's all about the supply of the system, because that's what you need to supply, and we very quickly focus in on the fan. Has the fan got enough pressure? Has it got enough flow? When in actual fact, the fan is actually the end of the equation in terms of the supply. It's more important to understand all of the downstream demand, what you're trying to do, what you're trying to achieve, and what other restrictions and influences you have there on the system. Okay, so as we look at the fan versus the fan system, you know, these are the sorts of things we need to start thinking about. So we need to be focused on the system rather than just the fan. Okay, well, what is the purpose of the system? Are we cooling, heating? Is it some process input? Is it some safety or waste extraction? And so what we're really getting at down the bottom there is, are we talking fan efficiency or are we talking system efficiency? And this is where there's countless examples we could use where having the fan at its most efficient operating point is not necessarily going to give you the most effective system efficiency. You know, really good examples being, if you take a dryer of some description where you're drying a product, you know, the way that you utilize the fan in terms of flow rate and pressure is just one of many variables. Changing your input temperature, your input humidity, and a number of other process variables can have a much more significant impact on the efficiency of your system in relation to just the efficiency of your fan, i.e. the efficiency of converting your electrical motor power into a dynamic dynamic power of air motion in terms of volume, flow rate, and pressure. So the key thing here is, well, what is the most efficient way of running our system, and how can we optimize that? So why do we want to look at this? Well, energy is just one of many savings, and that needs to be balanced against maintenance, capital, and the key really in all of this is there are so many examples where you can find what we refer to as the hidden plant, where you can realize additional capacity, whether that is just direct straight through capacity in terms of throughput. It may well be better quality or improving your quality, so you've got less rework involved, less downtime, lost production, improved quality. All of these factors ultimately connect. So, when we think about energy savings, if you're just thinking about the fan, you might have the most efficient point to run the fan, and it's going to be fairly a reasonably broad point where you can run that and have a reasonable efficiency. But then that efficiency is going to drop off. So that is something that you still need to be worried about. If it's oversized, we're going to run into problems. Equally, if it's undersized, we're going to run into problems. So the key thing being here, we need to think very, very carefully about understanding where our fan is at in relation to what we're asking it to do. Okay, so just talking for a minute about oversized fans. Why are so many fans oversized? Classic example here is when we build a facility or a process or put a line in, we're always thinking optimistically about where the future is going to take us. So expansion, and of course we always get the great deal from the supplier, where the difference in capital cost of fan A versus fan B that might be 1.5 or twice the size is quite marginal, especially when you think about all of the fixed costs and overheads associated with the project. That marginal cost of having a bigger unit is almost minimal. In some cases, it might even be the same price, and so the excitement factor of saying, oh, I can get the next size up. We think we're getting a great deal, and so we buy into this and we put the bigger unit in. We have the safety factors, things that we refer to as the anxiety factor. So we have the design engineer, we'll have a consultant, we'll have a supplier, or multiple people in the supply chain. And if everyone sizing the fan puts their little safety factor or anxiety factor in to make sure that the fan's going to be big enough, that the motor's going to be big enough, very quickly you get a safety factor on top of a safety factor on top of a safety factor. And as we do that, of course, the other thing is you might not have done a lot of detailed design to know precisely what your pressure drops are going to be, and so the lazy or poor design approach there would be to just sort of make sure we've got plenty of headroom. We don't want to be short of pressure. We want to have a bit extra flow, and so we overcompensate. And the reality is there is a risk versus reward scenario. Then, of course, you've got the key clincher with all of this, of course, is if you think about the different budgets as to who pays for the equipment versus who gets the return on an energy saving, different KPIs. Generally, your projects people are going to be rewarded based on finishing on time and under budget. And obviously, there's a real risk if something isn't big enough and it's not going to work, then obviously that's going to be rather career limiting. Okay, and so we often err on the side of caution. The problem arises, of course, when we err too far on the side of that caution. So what's the consequence of being lazy with our design or being too conservative? Well, ultimately, we're going to end up with an oversized fan, which is going to ultimately be inefficient and unstable to operate. We're going to have a lot of noise considerations. The fan may be running close to stalling. It might be pulled right back. It might be in an unstable part of the fan curve. Quite common to get pulsating flows. Our pressures might not be all that stable. We could be at a part of the fan curve where a small change in pressure can make a big difference to the flow rate delivered. quite common to hear people talking about ducts that breathe and oscillate. We can start to get vibration in our ducts and supports. We can have higher bearing loads and drivetrain stresses, increased duct leakage. Generally, if fans are oversized, we end up having to dampen back the fan to put the pressure drop up to restrict the flow, which means our static pressures in all our lines can be a lot higher. We end up with high static losses across dampers. Our fan might be running at low speed. Our motor might be at low speeds, which then has impacts on the long-term life of the motor. Ultimately end up with increased energy and maintenance costs. Now, interestingly, of course, so you think, well, okay, we've scared you off oversizing your fan, but then if we undersize the fan, then we also have other things that then come into the mix. So we then end up overloading motors, overloading bearings, more noise and vibration. Our equipment wear is going to increase. We then run the risk of having insufficient static pressure. We might start to choke our flow. And of course, as everything is pushed to its limits, we then have increased energy and maintenance costs. Potentially, the worst case scenario is where we may well actually lose productive capacity. And so obviously this is one of the key drivers why people tend to err on the side of caution and look to oversize their fans. But ultimately, the key message here is we want to get the fan sizing correct. Now, before we go into this example, I guess just on this point, if you get the fan sizing wrong, then you have a consequence of needing to compensate. Now, obviously, if you've compensated and had a rather large fan, we then start to take the approach, well, if we just put a bigger fan in and we hook it up to a VSD, then no problem. We can just slow the fan down as we need to. Problem solved. Well, as we think about this, I want to share an example. It was actually a 110 kilowatt fan. It was installed and runs about 6,000 hours per annum. It was massively oversized for the design duty. Now, as part of the installation to facilitate the ease of commissioning, there was a range of flow dampers installed in addition to the fan being fitted with a VSD. Now, what was interesting, of course, we had primary inlet dampers on the fan. We then had secondary flow control valves further down, as well as a primary flow control valve after the fan. And so ultimately we had a number of flow control dampers as well as a VSD. Now in this particular scenario, the fan was actually being run at full speed at 100% or 50 Hertz. So the VSD wasn't actually doing anything. Interestingly enough, of course, then your 2.5–3% losses across your VSD were being wasted for no reason. The fan could have been just DOL, direct online. Now, under this scenario, the combined total static pressure supplied by the fan was just under 8,000 pascals. And the fan was actually only pulling 60 kilowatts. Okay, the flow was a lot less than the rated capacity of the fan, with an annualized energy cost of about $36,000. Okay, so what was the opportunity? Well, first and foremost, with the use of the VSD, there was absolutely no reason for the inlet dampers or the primary control valves. And so by actually opening them up and in some cases removing them, okay, and then using the VSD to tune the fan, we're able to then also look at retuning the secondary flow control valves, and as it turns out, there was sufficient back pressure in the system that they weren't needed either. Our total static pressure drop went from 7.8 to 4 kPa for the same flow rate. And as a consequence, the power savings went from 60 kilowatts to 30 kilowatts, so 50% saving of $18,000 per annum. Now, a new plant built replicating this design was able to be built with a smaller fan, a smaller motor, a smaller VSD, and smaller cables. So getting it right also enables you to save substantially on the capital, reduces the size of spares that you need to maintain, and the irony or additional benefit in this particular situation is it gives you the option to still have additional capacity in the process as well without actually having a grossly oversized system. Now, in this particular instance, there were additional benefits where, as a consequence of solving some of these problems, the flow through the system itself was actually significantly enhanced and improved, and as a result, the actual process worked far more effectively, which resulted in increased yield and an increased quality on the product being produced. Okay, so as we think about this and as we look at the system as a whole, what we want to sort of really draw our attention to is understanding that when we talk about energy efficiency, we're talking about absolute energy efficiency of individual components, but then also the specific efficiency of the system. Now, coupled with that, there's a direct relationship with overlap with the reliability of the process in terms of that's going to impact on plant availability, the amount of time that your plant is on product as opposed to downtime or repairs, maintenance, etc. Then, of course, the other thing we have is in terms of the process reliability and efficiency. So what does that all impact in terms of our product quality and our process yield? And as you'll see, these various opportunity windows overlap and then obviously have some where they sort of have spillover benefits. And so there's a real opportunity here as we look at systems to think a lot more strategically on how we're going to justify improvements. Because ultimately, especially at the moment, we have very low oil prices and energy prices tend to be fairly modest at the moment. There's obviously talk at the moment about where the cost of electricity and so on is going, but nonetheless our energy itself is still relatively cheap, and as a relative cheap input, often the cost of addressing these things in isolation, the energy savings themselves aren't sufficient to provide the payback that we need. However, when you start to bring all of these other factors together, safety, environmental considerations, there's a whole host of other bubbles that you can intermix here. As you bring all of those opportunities together, the equation in terms of what you can justify and the merits for getting buy-in from across your plant and facility become a little bit more easier to manage, and obviously buy-in across the plant from operations, technical, environmental, safety. All of these people can become supporters of what you're trying to achieve. Okay, so as just a real talking point today, we want to get you thinking about, well, okay, for the plant where you work, what does your energy efficiency tree look like? We know everyone talks about the parable of the fruit tree, or in terms of all the low-hanging fruit that often people talk about. Now, is your tree a little like this, in a bit of a barren wasteland? Are you sort of in a bit of despair as to, well, what can I do? Or does your fruit tree look a little bit more like this? Okay, have we got fruit on the ground, lying around? Now, the interesting thing about the fruit being on the ground, it's rotting and deteriorating. Often they're savings that are sort of low level and are recurring. We have to be a lot more proactive and continuing to get that as it falls, rather than leaving it there for a while, because that's going to ultimately be a loss that we can't ever recapture. Then you have the fruit scattered through the tree. Now, we can pick the fruit up on the ground, but ultimately we want to introduce a bit more technology and start to harvest the tree. And so this is where we want to step up our efforts to sort of the next level. But ultimately, as you can sort of see with this example, our ladder isn't very high. And so we need to think about, well, how do we capture the fruit that's higher up the tree? Well, ultimately, what we need to do is, you might say, get a bigger ladder. However, as part of getting a bigger ladder, as we can see here from this example, takes a little bit more risk. We might have to go out on a bit more of a limb, figuratively speaking. I should point out at this point, I'm in no way advocating this sort of setup with a sort of step ladder on top of a ladder. The point being, as we go higher up the tree, there's a little bit more risk involved. Now, ultimately, what we want to do is have the right tool to achieve the job both safely and effectively. And this is where if you get the right cherry picker, we can harvest that whole tree, looking at it a lot more strategically, a lot more safely, and a lot more effectively. So what does this all mean? Well, what we like to do is we like to split up our 4 levels of energy efficiency. Okay, level 0 is what we refer to as our basic housekeeping. Now, there's a reason we call this level 0 and not level 1, and that is because ultimately this is basic stuff that should be business as usual. Often, we should be taking care of this. Now, too often it becomes quite reactive. We get into firefighting mode where it's sort of very reactionary rather than being proactive. And so really it's sort of the bare minimum that we should be looking at. Then we get to sort of level 1, which is sort of more where we start to get into sort of predictive programs as opposed to reactive programs. This is where we're starting to monitor and target our performance, standardizing our procedures, how we operate, how we maintain, how we tune, commission, and set up our process. Then we want to get a little bit further along and start to optimize our unit processes. And this is where we're starting to optimize, our fan and what it's doing, where it's going, with the temperature that you might be heating the air to, or how you're extracting, how you're utilizing, how you're recycling, separating, etc. Then ultimately the full level 3 side of things is where you start to look at the site-wide system integration. So this is where you're no longer just looking at the single system, you're looking at the total system. This is where you might have fan systems, pump systems, reactions, process vessels, process systems. All of these things come together, and this is where ultimately, if you're doing this process correctly, you'll become less and less concerned about individual technologies, i.e. fans, pumps, compressors, heat pumps, etc., reactors, and more interested in how all of these systems integrate together. So what are some real good examples here? Well, what we need to really start to get our thinking around is understanding this concept of individual unit efficiency. So we might have a fan, a boiler, a heat exchanger, a dryer, etc. They're going to have individual unit operation efficiencies, and obviously we want to have them, for example, the boiler operating as efficiently as possible. We'll then have process efficiency in terms of all of those systems' impact on how well we utilize our process, minimizing our waste, maximizing our yield, guaranteeing our quality, our productivity, and then looking ultimately at the end of the day at the total system energy efficiency. Now, as we look at this, what are we trying to optimize? Well, if you think about the product that you're making, whatever it may well be, you have a total embedded energy content in that product that you ship out the door. Now, the green component there on the right is the minimum energy content that you're going to need to make that product. Then your 3 blocks to the left, A, B, and C, are how we can break down all of the waste or inefficiencies built into our system. Now, the first one is really can capture or surmise all of the things that we do at the basic level in terms of how we look after the plant, our maintenance, our housekeeping. What are the things that we're doing that are just wasting energy because, for example, we haven't cleaned our filters for a while and so they're blocked up and so we can't get the flow rate we need, which is sort of impacting on what we can do in terms of capacity and quality, which has an impact on what we're producing. The second part is how we run our plant, i.e. what are we doing to operate our processes, our control decisions, what are we doing in how we manage our process, and are there things that we do that are actually costing us money in terms of, are we running things that we shouldn't, which are just wasting energy? Can we be a bit smarter? Then the third thing, and this is probably the most difficult to change in a lot of instances, there are losses built in when the plant was put together or the process was engineered, and this is obviously the more inbuilt these things are, the more difficult and costly they are to address or correct or try and improve upon. So from a fan system point of view, we need to probably start with the filter. So as we consider where our fan systems are on our site, we might have multiple systems. As we mentioned earlier, they might be in parallel, where we have multiple fans blowing air from common intakes or extracting multiple extraction streams from sort of a common reactor vessel or process, or they could be in series. So we might have some fans sucking and some sort of pulling the air or pushing the air through our system. Now they might have multiple sizes, they might be relatively small and modest, there might be just a simple HVAC extraction fan, right up to rather large, fans in the sort of the megawatts. Now, where do we start? Well, ultimately, we need to start by asking some key questions. And the first thing to really consider is, well, what are your systems costing you to run each year? You've got your energy costs, your maintenance costs, and then what is it in terms of downtime or lost production or lost capacity? It might be a quality issue that's causing you losses along the way. So it's about understanding the costs and how these are impacting on the business. Then, of course, you've got to think about, well, what are my barriers? Okay, and what are the impacts in terms of what we're going to do? So, we've got an energy limitations, we've got reliability limitations, there's costs, we've got process control, product quality. These are all the things that we need to be thinking about as we assess where our system's at and what our priorities need to be. It may well be actually that product quality is the best way to improve your effectiveness. If you're reworking a whole lot of product, ultimately the energy required to rework that product is going to far outweigh an incremental efficiency gain. And so it's understanding what the pressure points are. Now, once we understand those pressure points, we've also got some barriers to think about, well, what can we do? Is there a lack of awareness? Do we have a lack of expertise? Is it a lack of time, a lack of resources? All of these things come into the mix. It may be simply a lack of capital or a lack of support or a perceived risk that we don't want to change anything. Is the risk of change greater than the perceived benefit? And so this is where it's all about information and being able to understand and strategically weigh up the benefits. First of all, the direct benefits, but then being able to characterize those spillover benefits that we're talking about. Now, as we do that, we have to start thinking strategically, where are our assets? How many hours are they run? We want to be focusing on the plants that are running for quite a few hours as opposed to a few hours. What's the purpose of our system? Do we understand the control system? Is the control system effective? Is that what we need to address? Then as you start to dig in, you'll understand the true cost of running your system and where the opportunities lie. And then as we do that, we can ultimately identify our priorities in terms of size, or it might be in terms of the cost and the potential. And ultimately, we can assess what we can get done immediately and what's going to sort of take a little bit longer. And so this is where we come back to the 4 levels of opportunity. So level 0, as we mentioned, housekeeping. So then this is sort of something as you do a walk through your plant or your facility, what's the status of your filters? Are they looking a little black? Are they looking a little dirty? Is there a record kept when the last time they were changed? Now, have we got the sufficient sort of pre-filtering going on, especially if you've got dusty environments? We're coming up to summer, and as summers invariably do in New Zealand, things are going to dry out. Things are going to get dusty, especially depending on which part of the country you're in. Talking about El Nino and so forth, and having a sort of a hot, dry summer, there's going to be consequences, and what do we do to ensure that we're on top of making sure that our filtration is effective and adequate, and that we've got the right cleaning regimes or replacement regimes for our filters. Ductwork, have we got material building up in our ducts that become a problem in terms of blockages? Have we got material building up on impellers? Now, there's not just an energy impact there. It might also be a safety, an imbalance problem might come into the mix where you could potentially do some serious damage to your equipment. So understanding the degree of cleanliness that you need in your system, and obviously, you know, a food plant might have a more stringent requirement than sort of say a low-level sort of extraction plant. However, having said that, on an extraction plant, if you're extracting, say, a sawdust or some other material, you know, a building up of that material in ducts can be a major safety hazard, fire risk, you know, so there are a number of things that you probably need to think about. Now, from a rotating equipment point of view, you've got the maintenance of bearings, pulleys, belts. You know, are our belts correctly tensioned? Are our running gear properly aligned? Are we using the right pulley ratios? Are our speeds where they need to be? You know, all of these things in terms of keeping an eye on the system. Now, you'd like to think that all these things are being taken care of. However, you know, who is asking the question? The other thing that's a really, really common fault, and you see it all too often as we go out and about to various sites around the country, both here and overseas, it's very, very common to see your flexible socks around duct transitions and the like, that these things have big gashes and holes in them. You know, how well are these being maintained? Now, there's, you know, an energy loss point of view. Are you sucking in cold air into a system that you perhaps won't want that cold air, and is it causing cold spots, or conversely hot spots? Is there, never mind an energy loss point of view, but is there a product quality or a safety issue associated with that? It's very, very common, you know, these basic things that are, you know, relatively easy to get right. Are there other parts of the system, various components that need to be maintained, or are they not being maintained as well as they should be? Is there coils or fins and heat exchangers that have vibrated loose or have worn, and obviously you've then got potential contamination and so forth. So these are all the basic housekeeping opportunities. Now, once we get past that, we then start to move on to what we refer to as our level 1 opportunities, and this is where we're looking at the fan and the system control. So have we matched the fan and how we operate and control it to the system demand and what we need it to use? Are we operating the system correctly? Have we got the right control variables? Are we using dampers where we shouldn't? Can we use VSDs more effectively? Flow dampers can cause significant obstructions, and one of the interesting things there is what you need to be very, very careful of is it's very easy to have material build up downstream from these obstructions, because you get eddies and vortices generated that create dead spots in the duct where material being conveyed can drop out as the flow rates drop. With unnecessarily flow obstructions, we get more back pressure, which is obviously going to limit the capacity of our system. From a fan control point of view, can we tune the fan? Is there a pulley change that can get us a better operating point and move away from using flow dampers? Can we use or better utilize or install a variable speed drive? Do we just need to get the right impeller? Could be as simple as you want more capacity, you might be able to pull out the impeller and get a slightly bigger or wider impeller. It might even entail a motor change, but that might free up capacity that you require. Okay, so once you've looked at all of these basic level systems, we then start to get a little bit more involved in looking at modifying the system. Now, as we modify the system, we're looking at, you know, ductwork modifications. Are there transitions that are causing us problems? Are there fan intakes or exit configurations that are not well utilized? Can we optimize our system? Are we using the right temperatures? Can we increase our temperature for our process rather than a flow rate? Are we using the right mix of flow rate and temperature? Can we rebalance how we supply the required heat load or cooling load that we may need? Are we using or have we got good airflow distribution or gas flow, depending on the nature of what it is you're controlling? It's very, very common to have poor ductwork that results in very poor distribution, which then has a knock-on effect to the performance and efficiency of your process. Are there more advanced system control strategies and techniques that can be employed to better optimize and utilize your process? So here's a couple of really good examples. So it's very, very common to see bends right at the intake of a fan, which has a massive knock-on effect to the performance of the fan, and then obviously the downstream effects as well. I've seen really bad cases here where you can have really bad induced vibration causing ductwork and walls and the like to vibrate and destroy themselves very, very quickly. It's not uncommon to see cyclones jump up and down vertically, sort of 25 or 50 millimeters. All because sort of the duct design and the airflow hasn't been engineered correctly. So if you do have to have a duct really close to the fan, you want to think about what do we do to ensure that we get good airflow coming in. So whether we change the duct on the bottom left there, or do we need to put some flow straighteners to help the flow come around these bends. Another example on the outtake of the fan, where we have ducts splitting off after the fan. It's very important to get the location of those offtakes correct. We have the example on the right there. You want to give the flow coming off the fan a chance to expand and get good static pressure recovery, and obviously better mixing of the flow. There's a great Department of Energy fan source book that's readily available online. If you look for the link, feel free to email me and we can point you in the right direction. Another really simple example, but fans, when they're specified and selected, you can generally specify the orientation of the fan, and you talk to a lot of people, and it's not uncommon to see a lack of appreciation of the significance of getting the rotation of the impeller aligned with both not only the incoming duct but also the outgoing duct. So you can see on the left we have the fan putting a rotation on the airflow, which is going in the opposite direction to where the duct is going to go. So ultimately we have quite a lot of eddies and flow separation, and obviously ultimately a static pressure loss, which impacts not only in energy but also potentially on what's downstream of this stuff. This is then feeding into a filter or an attenuator or some other device that can impact on the distribution. The attenuator is not going to work as well as it should, or the heat exchanger is not going to work as effectively as it could. Whereas you can see on the right, we've got the air rotating counterclockwise, and then obviously the duct work is aligned with that. So, it's the little details in terms of getting the specification of the fan right. You can place the fan inlet too close to a T-junction in a duct and get all sorts of competition going between the two sides. The flow is going to be turbulent, it will be unsteady, and so as such you're going to get a beat pattern happening at the intake to the fan, will impact not only on the performance of the fan but also on vibration loading on the ducts and anything that then is connected to. So if you've got a tight space, it's very important to segregate. You can see this big black mark in there, the two flows, so that you're directing the flow into the fan. Now, once you get past all of these basic duct and configuration opportunities with the system, you can then start to consider the full system optimization. So is there opportunities to redesign the process, look at how the gas or air is used, plant layout, duct layout, temperatures. Have we got the right set points? Do we need to look at changing that? Do we need to tune our process? We can optimize our system. From a best practice point of view, are we using the right equipment? Have we installed it correctly? Have we got the right controls? Have we got the right maintenance practices? What are we monitoring? There's condition monitoring that we need to think about. What are the KPIs? Is it more than just a pressure or a flow rate? What are the other things we should be looking at? How are we linking that back to quality and yield and so forth? So indicators of an inefficient system, just to really summarize in terms of getting started, and what are the things you really want to look at? What are the easy gains? So dirty filters, general cleanliness is a real easy gimme. If you've got flow control dampers that are even 45% open, 50% open, to even worse, perhaps even more closed than that, that's an indication that you've got an opportunity to do something. You might have primary dampers and secondary dampers. You might have poor duct transitions. If you've got a high duct vibration or noise levels, it's time to go and look and start to investigate what's causing those vibrations, what's causing that noise. generally there's going to be something that's upsetting the system. If you have high static pressures, if you're up over the sort of the 4,000 pascals, up to sort of 8,000 pascals, and all you're doing is moving air around the system, chances are you've got a problem that you need to sort out. If your cyclones typically have a pressure drop of more than sort of 1,500, 1,800 pascals, chances are it hasn't been set up correctly, or it's undersized. Bag houses, once again, depending on the nature of the application, obviously, but if your static pressure loss across your bag house is more than 1,000 pascals, you've probably got an undersized bag house, or you're not getting good distribution across your bags. If you've got leaking socks and ducts, these are all telltale indicators that there's some easy opportunities to dig in and get sorted. So where to from here? Well, first of all, the material is going to be available for download. There's more webinars to come, and in the new year we'll be getting into more advanced topics to really dig your teeth into and on a range of areas, and sort of getting into detailed case studies. On October the 14th coming up, we have pump systems. On the 28th of October, process heat. The 11th of November, process cooling. 25th of November, steam systems, and the December 9th, compressed air systems. So if you want more information on the webinars and how to register, that can be found at the website energyefficiencyNZ.com. Will also be available on the EECA website. Now, at this point, another reminder here is that the EECA business program are supporting this, and any advice or support in getting started on projects, implementing or trying to identify things that we've sort of talked about today, or anything else for that matter, your EECA account manager is there to help as a first point of contact, or you can visit the EECA website and there's a number of useful links there. And just a side note there, we have webinars will be available for future viewing. So that's where you'll have the slides and the audio. So this is new this time around. So it's something everyone's been asking for. So we're going to oblige. And so yes, so that will be available. So like I said, our website there, energyefficiencyNZ.com, has more information available. Well, that actually concludes our webinar today. I'm happy to stay on the line and answer any questions that people may have for a few minutes. It's been rather conspicuous in the absence of questions coming through this morning as we've gone through the presentation. I can appreciate it's a bit of a generic overview to get started, but we'll stick around for a few minutes if anyone has any questions. If you've got a mic, we can give you a mic and you can have your say. So on that note, feel free, we'll hang around if you want to fire through any questions. No need to be shy. Okay. We'll give you a few more minutes. If you're still thinking or typing, we'll be on the line for a few minutes. So feel free to fire any question if you have one. Okay. Okay, we've got a question here. Oh no, very good. Thank you, James. We appreciate you being on the webinar. We'll talk to you soon. In answer to your question, Keith, yes, the presentation has been recorded and it will be available as a full download, both slides and audio. So by all means, feel free to share and sort of use this as a good talking point within your organisation. It's a very good question to ask. Obviously, with the download, if you're looking to sort of use it as a talking point, that will be readily available. Okay, well, if anyone else has a question, we'll give you a couple more minutes, but failing that, otherwise you can, as soon as we've got the download available, we'll email out to everyone today and the link so that you can have access to that. I will give you guys one more minute if you want to fire in a question. Otherwise, we'll wrap things up and stay tuned for the next webinar in 2 weeks' time. All right, guys, we're going to wrap it up there. If you have any questions, feel free to send an email through offline, and we'll happily assist if we can in any way. So thank you very much, and we'll see you in 2 weeks' time.